Great. So I'm Steve Brierley, CEO and founder of Riverlane. At Riverlane, we're working on quantum error correction. So that's the critical enabling technology that enables quantum computers to scale up to utility scale and to have the impact that we all see and envisage for quantum computing, whether that's in drug discovery or the design of new materials or new chemistries. Quantum computers will be a tool that unlocks many world-changing capabilities. So there's kind of three things that I'd like to get across today. The first is that Riverlane is a classical semiconductor company, so we don't build any qubits ourselves. We design the chips, which together with our software solve real-time error correction. The second thing is that now is the time for quantum error correction. We've seen a huge number of breakthrough experiments in quantum error correction over the last 12 to 18 months. This is really the moment of quantum computing hits this inflection point where quantum error correction allows these systems to scale up. And the third point is that there just really aren't enough people who understand quantum error correction, and that's a problem that we need to solve. That's why this talk is about building a developer community. We need the tools that enable people to upskill. We need to better understand and explore how error correction works and how to implement quantum error correction. So I want to start just with a very quick summary of Riverlane and kind of where we are today. In 2023, we released the world's first decoder chip. So we showed that we could decode at a rate of megahertz, keeping up with the data generation rate of quantum computers. In 2024, we embedded that technology into Rigetti's system. We showed the world's first low latency quantum error correction experiments, so decoding in microseconds. And then in 2025, we made that technology available to the whole ecosystem. So we released a second generation product that you can now couple into your control system to implement real-time error correction. So we're 120 people, so I definitely know about this problem of finding top QWC talent. We combine leaders in quantum error correction who worked at companies like IBM, Google, AWS, with world-leading chip designers. So bringing together the semiconductor expertise with the quantum technologies to turn quantum error correction, which has been a theoretical idea for many decades, into a technology. So last year, you saw three major breakthroughs. I'll just call out these three. I mean, there are certainly many more, but I think kind of notable ones. So you've got Google demonstrated quantum error correction on the surface code, showed that you could go below threshold. Quantum error correction actually works, right? That was really the result. The second result I wanted to highlight is the paper that we published with Rigetti. So we showed that you could solve this problem in real time, and this is a fundamental building block into building fault-tolerant systems. And then the third paper to call out is on neutral atoms. So this highly flexible system that Harvard developed was able to implement logic across a large atom array. Now, all these results kind of come together, and I've got two plots here. So the one on the right-hand side, sort of number of implementations of quantum error correction over the years, and you can see it's going up pretty quickly. And then correspondingly, the number of tools that are being released and the usage of those tools. So this is kind of tracking GitHub stars of some kind of widely available open source tools that cover things like simulation and decoding and so on. But as I said at the top, the main challenge is the number of people in the world who understand quantum error correction. I'd estimate that's approximately 400 people. But 95% of people think that quantum error correction is the most important challenge. So if we're going to reach utility scale quantum computing, we're going to need a lot more hands on deck. We're going to need to train these people up. So we partnered with the Unitary Fund to kind of understand this better, like why are there not more people in the field? The top three reasons are just insufficient training, lack of knowledge about quantum error correction, difficulty in securing resources and support to do it, and a lack of clear guidelines or best practices, right? And so this is a problem that we want to solve, and I'll talk through how we did that. So I thought the way, in implementing this paper with Rigetti, we learned a ton of things. So So what I want to do is just talk through what did we learn when we were implementing the error correction on the Rigetti system, what tools did we need to build in-house, and then what we've done is make all of those tools available to everybody so that you can all now recreate that same experiment. So I won't go into the full detail of the experiment, but I think running any QEC experiment essentially has three main phases. So the first is to generate your quantum error correction circuit. So you're trying out different codes, you're thinking about how you're going to do syndrome extraction, you're trying to figure out what happens if one of your qubits is a bad qubit, how do you work around that. The second step is to then run your real-time error correction experiments. So implementing those circuits on the quantum computer and analyzing the results then becomes the third step. So let me just talk through each of these in turn, just to give you a sense of what's happening. So here's our experiment with Rigetti. You can see this was on a 60, 70 qubit chip. We identified where on the chip we were going to implement the circuit. This schematic shows you kind of the syndrome extraction circuit in particular. And this involved using STIM, which is a simulator, a Clifford simulator developed by Craig Gidney, and exploring various different codes for extracting the syndrome data from the quantum computer. It also means kind of setting up the QWC experiment and figuring out kind of what's the logical operations. So then the next step was to actually run that, right? So now we've got our circuit that we want to implement. We now need to map that to two things. So one is the control system. So the control system's got to trigger the physical pulses. It's going to implement the physical gates on the quantum computer. And then the second bit of data needs to go to the decoder. And the decoder then knows what to expect from the quantum computer as the QEC experiment is running. So these two bits of information are generated. You've got to map that down to the, for example, the native gate set, and then you have to increase or tightly couple the communication between the control system and the decoder. And then the last step was to analyze the results, right? And of course, these steps go around in many iterations, and you're looking at things like IQ plots and logical error rate probabilities, and you're really hoping for this final plot up at the top, this signature that quantum error correction is working, the logical error rate's going down as you do more syndrome extraction, right? So this is when the team starts getting really excited, right? So you're really then trying to understand things like the correlation matrix and the error budget, like when things are not working, why they're not working, and this whole loop goes round and around. So yeah, I'm delighted to say that we are today releasing DeltaKit. So DeltaKit is this essential toolkit that wraps up a lot of the tools that we developed in order to do these sorts of QEC experiments. It's an open source package that enables developers to test, run, analyze logical circuits on quantum computers and on simulators. It's highly modular, so if you can take the bits you want, you can develop other ways of solving the problem for other parts, really up to you. It includes the ability to explore novel error correcting codes. And I think at this stage, we really don't know the best way to do quantum error correction. We're really in this exploration phase. So it's a highly flexible toolkit. It has realistic noise models inside, so you can get a much closer sense of like, how is this actually going to run on my quantum computer, and better understand when the results are different, why are they different, like what's really happening. And then it has the basic building blocks for things like stability or for memory experiments, and then it allows people to develop their own building blocks for these core functionality that's going to go into a fault-tolerant quantum computer. And I think the really nice thing about this is it's the first time it brings together all of these tools. So parts of this have been available before. You can hack together combinations of these. But I think the really nice thing about DeltaKit is that it's an end-to-end solution that allows you to run your first experiment in quantum error correction. We really want to lower the barrier to implementing quantum error correction on these quantum computers that are going to be made available over the next few years. So we're releasing DeltaKit along with the DeltaKit textbook. So this is a hands-on introduction to quantum error correction. It's going to help get people started and up and running as fast as possible. Again, there are various different tools out there, or, ways of learning about quantum error correction, but there's no single place where you can get started on quantum error correction. So that was a problem we wanted to address. It was a problem that we've seen again and again in the company. The more people we hire, the more people we're training. And so these are really tools that we found incredibly useful ourselves and are now available. I think this is going to be useful for quantum computing companies who have their QEC teams and they don't want to spend their whole time training the rest of the other QEC team. It's going to be useful for high-performance computing centers. So we partner with organizations like Oak Ridge National Labs, for example, who are leveraging high-performance compute in order to really kick the tires on approaches to reaching utility scale. And it's going to be useful for research organization, both in education and in research. So yeah, really delighted to release DeltaKit. You can see there's a link to the page here on this QR code. We're building it with a great ecosystem. We did a soft launch at the QEC conference a few weeks ago and had over 100 developers sign up already. So yeah, really excited to see kind of what people build and to see what you're going to build with it too. And with that, I'll say thank you.